Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, I'm Doug Berger. I'll pass on the opportunity to say anything inappropriate given there's only a few people in the room, but there may be people watching online. So it's my pleasure today to introduce Hadi Esmailzadeh. How's my pronunciation?
That's perfect.
Okay, thank you. I try hard. Hadi is a PhD student at the University of Washington who started with me at the University of Texas, moved to Washington, is now working with myself and Luis Ceze and several of the other graduate students in Luis's group. He has had an amazing track record of output and top quality research over the past couple of years.
Thank you.
With several award papers mentioned in the front page of the New York Times on your work. And he's now has an incredibly interesting result in a new area that we believe is going to be very important. And it's new, it could be profoundly important, it could be completely irrelevant, we just don't know, but it's very exciting. So thank you for spending your summer here with us doing your internship. You've gotten a lot done, and I'm really looking forward to seeing the results of all your hard work.
Sure. Okay, good morning. Today I'm going to talk about a new class of accelerators that use machine learning to accelerate approximate general purpose programs. This is a project which is done in collaboration between University of Washington and Microsoft Research and the University of Texas at Austin. I have collaborators from these three institutions. Parts of this talk is going to appear in the next International Symposium on Microarchitectures. So people have been using accelerators. And there are different kinds of accelerators like GPUs and FPGAs that each of them take advantage of certain characteristics in the program to accelerate the programs. Like FPGAs can accelerate applications that have abundance of parallelism, but they are compute bound. And GPUs are good for applications with a lot of parallelism, but they can't, work well with the applications that have very divergent control flow. And there has been recent, proposals in the literature for different accelerators that augment a processor and try to, let's say, synthesize parts of the program on hardware or use a configurable fabric to actually accelerate the programs. What we are looking here is that, we want to take advantage of this characteristics in many applications in diverse domains that full precision is not always required. Either there is no certain one answer for the application, or a little bit of error at the output. The best example is graphics, and we see it like in JPEG compression, is tolerable, and the perception of the human plays a role in this process. So,
I have a question.
Sure.
Why is it your belief that the opportunities for approximate computing and applications have increased?
I think because machine learning and is taking over, and we are facing the era of big data. That we need to do a lot of computation with a vast amount of data.
Then your applications are drawn from big data, really.
Search is one of them. Or if you look at data mining.
No, I'm talking about in your paper.
Right.
But so I guess the root of my question is, has there been some trend that is making approximate computing more possible? Or is it the case that we could always have done it for example, HPC workloads and numerical simulations, with convergent algorithms, gradient descent type approaches, and we've only just realized this now, or our backs are against the wall? I mean, has it always been there, or has it grown because of the emergence of some of these areas?
So there is another trend that is emerging. Maybe it's because of the challenges that we face in the silicon.
That's not driving the applications.
Right. That's like, that's the energy
It's
efficiency.
limit what applications we can do and drive them that way, but that's not what's driving a lot of these. And big data is a buzzword. I mean, yes, it's important, but
Right.
so do you think something has changed?
In the application domain.
Are there a few obviously identifiable trends? I mean, machine learning is clearly one.
Machine
More
learning
popular,
is
but-
one of the things. And then, so another trend that we can maybe look at is doing computation with limited amount of energy, and then trading off trading off battery or harvested energy for the quality of results that we
That's an
can.
opportunity, but that's not what's driving a lot of these emerging applications today. Vision is emerging despite energy limits, not because of it.
Right.
Okay, let's put that on the queue.
So isn't it that algorithmically things like approximate algorithms are gaining in their acceptance and in use of these things?
That might be
Is
the
that-
case. That might be the case because a lot of let's say recognition or even gaming, they don't require in algorithmic level. They don't require like perfect
And those are used to help reduce overall computation time or
That's
prove
true.
various properties about
That's true.
convergence or things like that.
Yeah, but I'm not sure if that answers Doug's question.
I just wonder if it's that if you're summing up your checkbook, you want it to be precise, but whenever you're interacting with the real world doesn't have a precise digital representation, and so there's necessarily going to be fuzziness. So as we do more things that interact with the world, vision, augmented reality, trying to extract trends from the web, they're all in some sense approximable because they don't have a precise answer.
You could also go and say that there's an acceptance of doing that. So 10 years ago we were working on compression of NASA images and the answer was, yeah, you could do it, it doesn't hurt the algorithms, but they wouldn't accept it because, ooh, it's not exact and therefore it's wrong. And I don't know if that's necessarily the case anymore.
Well, they're older now and their vision's gotten worse. They can't tell.
Yeah.
Okay, so what we are doing is that if we look at this design space of processors, we always trade off power and performance and move over different points in this design space. Each point in this design space is a processor, and the line shows the Pareto frontier. What we are doing is that we are exploring a new dimension, which is approximation. And what we want to do is that we want to compromise a little bit of accuracy and hopefully get better performance and lower power by compromising the amount of accuracy. And for this, we are proposing a new class of accelerators that need to be trained rather than be programmed. So what I mean by trainable accelerator is that if you look at an imperative code, you pick a target region that is hot, and it's like the application spends a lot of time on it. Then put a learning algorithm besides it, run the application. The learning algorithm will observe the inputs and the outputs from that target code. And after it reaches a certain level of accuracy, then you replace that target region with a recall to that machine learning algorithm. So we call that algorithmic transformation a Parrot transformation, which mimics the target region of code. That allows us to run the program on the core, on the processor, while accelerating the machine learning algorithm on a dedicated hardware. Since this is replacing that target region, we are indirectly accelerating the whole application by doing this transformation. Sure.
Do you ever learn the regions that you shouldn't apply this and drop back to the old code for those situations?
And so we have safety criteria. Like, let's say you are doing JPEG, right? So when you are writing the header of the JPEG, right, it should be precise, because if you even like mess up one bit, the image is not unreadable. But when you are processing the pixels and the bits, then you can do approximation in that code. So what we require from the programmer is to annotate regions of code that are approximable, without being conscious about which technique of approximation we are going to use. Just tell me which regions are safe to approximate and have a little bit of inaccuracy and error at the output.
So using your JPEG example, do you have a notion of a quality factor? Like JPEG compression, I can set a quality factor on the compression, or are you so small in your approximation that it's just a little bit of noise around this coarser grain?
That's an interesting point, but right now I don't have it for this technique. We have other techniques to use, different approximation methods that we can actually tune up the approximation, but not for this.
There's a whole body of work on synthesis where programming by example is becoming kind of in vogue, right? And I'm really struck by your title here, accelerators should be trained and not programmed. You could almost, using some of the ideas from Sumit Alwani and Raz Bodik on synthesis here, you could thinking about programming in general for a large class of programs as being trained, not programmed, right? You specify very simple, poor quality algorithms and then train whole bodies of work, and it's not really necessarily about accelerators. Your accelerator now here is just a general CPU, right?
Sure.
So I think the generality here is great.
That's actually very, very interesting.
So how do you, sorry,
Sure.
can I ask this? It's really interesting. So I think when we get a little bit deeper, we do have a non-CPU accelerator, but how do you tie program synthesis to this training that you can use to make things more efficient? Paddy's doing this algorithmic transformation. Is there a tie there, or are they just intellectually interesting?
No, I think there is a tie. I mean,
Yeah,
you can think about synthesis as training, right? So the programming by example, that's examples much like you have a learning problem here.
Yep.
And in the same vein, those examples are used by the synthesis engine to come up with a huge, you can think about synthesizing a large number of possible solutions and picking the one that balances approximation for versus power.
I see. So it's more like we can think about the ones that are most amenable to this transformation.
That's right.
Okay.
But for general purpose code, right?
Right. Are you going to remember that?
Yes.
Okay. I'll take it
Can
out.
you actually hit me like links and
Yes.
papers?
I'll talk to you afterwards, because I've been actually working on a similar problem for synthesis in this example.
Oh, okay. That would
This
be
is
awesome.
awesome.
Yeah, this
All
is
right.
awesome.
Great.
Your talk's already a success.
So to do the Parrot transformation, so this has been an internal debate between me and Doug about the naming of the Parrot transformation. So if you have better suggestions, I'm willing to hear.
Who likes Parrot? Who doesn't like Parrot?
I like the Parrot. He doesn't like the Parrot
Parrot's
transformation.
Yeah, I like Parrot.
Screw you guys.
Talk to the empty chair.
So to realize the Parrot transformation, we actually, we need to come up with a learning algorithm that can learn regions of imperative code. And then we have to come up with a programming model that lets the programmer, think about this transformation and annotate the code for us. And then we need to come up with a compilation workflow that actually carries out this transformation. And then we need to think about the implementation of that learning algorithm. As I'm going to show you, and I think I gave it out with the title, is that we empirically found out that neural networks can actually mimic parts of the imperative code. And the good thing about neural networks is that we know how to implement them very efficiently in hardware, and they're inherently parallel. So they're a good target for the acceleration at the end. And I'm going to talk about different opportunities that using neural networks will provide us. But in general, I think potentially any regression mechanism can be used for Parrot transformation. I don't know if it's going to be beneficial because I haven't tried them, but I think potentially you can regress any region of code with, let's say support vector machines or logistic regression or any kind of these transformation to do this. So first, let's talk about the programming model. So the developer should be involved because of the safety. As I told you guys before, it's important because programmer has the only view which part of the algorithm is safe to approximate. So the programmer needs to annotate the source code. But which kind of source code is good for Parrot transformation? So aside from the being approximable, that needs to be hawk code because we want to we are bound with Amdahl's law, and since we are limited by the topology of the neural network when we are doing the Parrot transformation, that region needs to have fixed size inputs and outputs that I can, as a compiler, identify at the statically at compilation time. So let's look at an example. So here I'm showing a Sobel, edge detection algorithm. So what you do is that you take an image, you convert it to a grayscale, and then you slide a window over it, and you do the convolution operation. The convolution actually estimates the gradient for one pixel with respect to its surrounding other 8 pixels. So it's inherently approximate. So the programmer is going to do an annotation that this is approximable. The programmer is not aware that I'm going to use neural network. Just this is approximable. And this is a good code because it has fixed number of inputs and just one output. So what I'm going to do the Parrot transformation in 3 steps. The first part is that I'm going to take the annotated source code, put probes on the inputs and outputs of the candidate function, run it with a certain number of input data, collect the training data, which are the inputs and outputs to that candidate region. Then I will feed that training data to Parrot generator, which is going to explore the topology space of neural networks. And we do a search space. We have a search space of neural networks, and we try to find a neural network. And that Parrot generator is going to give us a topology and then a number of weights. And then we take that annotated source code again and take the neural network and replace the calls to that candidate function with the calls to the neural network. And if we have a special hardware, right, we are just invoking that special hardware behind the scene instead of running the original function. So in our example, our Parrot generator has found that 9 to 8 to 1, these are the neurons, these are the inputs, and that's the output neuron. That can mimic the, that region. And, so what happens here is that instead of calling the original function, I'm sending the inputs to the neural network and receiving the output instead of that. So if we run this on an image, the neural network is trained on a different image. And this is the running it on original code. This is running it on a Parrot transform code. There are a little bit of difference. I don't know if you see it here, but I think perceptually this passes.
Can I ask a question?
Sure.
I mean, I realize that you're looking at applications where there is this kind of perceptual aspect to it, but because you're just doing transformations, right, in these ops, is there any way to reason about the error bounds?
Yes, so for the neural networks, I'm going to show you like different applications and how we use in the bot. Like, so this is a good example for showing to the audience. But you can reason about the error of the neural network. Its standard is MSE, minimum squared error. And then for the application level, depending on the application, you can define an error metric, like an average error, or root mean squared error at the application output level, and see what, so that gives you a mathematical framework to reason about the error in the application level.
If you couldn't do a max error.
You can define, so it's your, as a developer, you can define any error metric that suits you, right? You can do maximum error, and if it doesn't,
You only do maximum error over the training set, not over any possible input set,
Right.
I would assume.
so when we are doing this, we have an input for training. We have an unseen input for test and evaluation. So you define the error metric for that test and evaluation metric, for that test and evaluation data.
But you could, if your data set never passes a negative number to square root, you will never know that the code needs to see that and flag an error in either of the sets, but later on it's a difference.
Right. So I can't, so like similar to any applications that use learning, I can't, bound the error and say that I will mathematically guarantee that the error is going to be less than this. What I can do is that I can say that that's going to happen infrequently. And hopefully, since your application is approximate, the final output is still going to be okay. But we can do one more step, right? We can put the NPU and a predictor, right? Which predicts if this error is going to be too large or the input is unseen, right? And then decide if I should retaliate the original code instead of running the NPU. So that's one of the approaches that we are thinking about. I haven't implemented it yet.
You can also do it after the fact too, right? And throw an exception, right? And then
Exactly.
And then use the original semantics.
Exactly.
Yep.
Exactly. That's actually done. There is a work called Relax, which does approximation for different regions of code, and they throw an exception and retaliate back if the error is more than a certain level. So another application is inverse kinematics. So you have a two-joint arm, and you have the x's and y's, and you want to figure out the angles of the joints. If I can play this, that would be awesome. Okay. The circle is the original application, the original code. But the arm is moving with the Parrot transform code. So we applied this to 6 different applications. For FFT, from signal processing, inverse kinematics, robotics. I didn't do 3-joint arm because 3-joint arm doesn't have a closed form solution, and the speedups are huge because you can just learn where the arm goes. We did it for part of the JMonkey game engine, which you figure out if 2 triangles in the 3D are intersecting or not. We did it for parts of JPEG. We used it for k-means and the Sobel filter. For k-means, to make it easier to understand the errors, I used k-means for image segmentation. And these are the neural network MSE errors. And these are the application level errors, the VC. For FFT,
What does it mean? What's the application level error?
Right.
What does that
So for FFT and inverse kinematics, I use the relative error as the metric. For JME, either you're hitting or missing if 2 triangles are intersecting or not. So this is the miss rate. And for JPEG, k-means, and Sobel, I'm using image difference between the original application, original code, and the Parrot transform code. at the output. The pixel differences. Average root mean squared pixel differences on the output.
For JPEG, is the error usually like clustered to a few really bad ones, or is it just kind of a smooth error?
It's a smooth error. It's a smooth error. So we can do Parrot transformation, but what opportunity is there for when we are doing the, Sure.
Sorry, can you go back one slide?
Sure.
If I were to do a normal JPEG compression to an image, do you have any idea how that relates to your error metric?
I haven't measured that.
Okay.
But this image is worse than normal JPEG.
Okay.
So the
Significantly
quality.
so, or I
What's-
mean, is it something you can visualize? You can see the difference, or is
I
it,
can visualize the image difference and
Okay.
see how that looks.
Can you post-process to compute a quality factor with JPEG? Like with the final
Yes.
compressed images to
Yeah, yeah.
use their metric?
Yeah, actually, the average RMS error difference is the image difference that image processing people use. That's the reason I used it. And this is between after you do the JPEG compression, and then you do the Parrot transformation, you see like an average of 10% error. So now that we have this Parrot transformation, we can have different implementation of that neural network. We can have as a library, I can just call a library of neural networks. Or I can use digital NPU. And this should be analog, sorry, I fixed the graph, but I didn't update the. Yeah, so this should be analog. That's what. Yeah. So that's why I came up with this idea because I wanted to do analog computation while having digital normal programming interfaces, but use analog circuitry. And there is a whole body of research that shows we can do analog implementation of neural network. So we can use analog, and I'm going to talk parts of it. So let's do the software first and see what happens when we do the software. So if I use a library, this is I'm using this is application Slowdown, and this is the different applications, and I'm using FANN, Fast Artificial Neural Network. It's a widely used open source library, C++ implementation. You see that this is kind of at least the CPU implementation is not working. But I did these. Sure.
What? This is, if you do your technique, how much the code slows down?
Yes, if I just use a library of neural networks without any hardware support.
Fact, go ahead.
This is how not to do approximate computing.
Yes.
Hardware support.
Well, but you leak a lot more, and so you consume a lot more energy because you're running so slowly, and so it's a huge opportunity for speedups and improvements.
Okay.
Change the denominator.
Straw man.
It's like power consumption branch predictors.
Right. I'm trying to make a case for two things. Right. One is that how can we change the processors so that we can, we can actually gain benefit from this without adding any extra hardware to the processor, without adding the actual big accelerator to the processor. No algorithm changes.
Okay. Can we flip back one, please?
Sure.
Does the difference in the heights relate to the size of the input or the computation size, or what's the difference between 5 and 75 typically?
So it depends on how much of the computation goes into that region of code, right? So in the FFT, we are spending 30% of the computation in that region. So I'm slowing down that region, and then Amdahl's law translates to this 4.5. In JME int, that region is most of the application, and the implementation actually is based on a paper that is a very efficient implementation. And I'm using a large neural network because it's a very complicated control flow intensive region to emulate that, to approximate that region. So I'm trading off a little bit of computation to a large but regular computation. So I see a huge slowdown. Does that make sense?
Yeah, I guess I was expecting a statement along the lines of, if as the number of instructions I'm replacing goes up, my penalty goes down, because the ANN is sort of fixed time. So you want to increase the amount of code you cover.
Exactly, that's one of the things. But there is another side to it, is that how much computation you are replacing that region. Right, as you enlarge the region, then the neural networks potentially can grow, and you may not end up with a gain there.
So the example you gave where you had the approximate annotation on the code didn't have a loop, I don't think. It was just straight floating point computation. If I have a loop, then I could potentially have a program that doesn't terminate. And so I'm trying to get to the point of, when does this break down, and when can you not learn a particular function? Have you guys tried to classify? I mean, effectively, you can reduce this down to the halting problem, I suspect, right? Because now you have a neural network that's going to try and tell me whether or not my program halts.
Right.
So when does this break down, and when can you? But for some programs, I can actually deal with loops.
Right. For JPEG, there is a loop inside that goes over the pixels of like 64. You don't like implement it in a linear, but it's not a loop that goes around for everything. So the region of code should not change any states besides its outputs. So the neural network that I am replacing that region of code, right, takes a bunch of inputs and generates a bunch of outputs, right? So, and if that code is changing something besides the outputs, either I have to hoist it and do a bunch of computation to come up with it, so that this region of code is pure, or I can't do it.
I think it's a much simpler answer. So you can, slap me if this is just way off base, but I think you can. I'm going to move to the side here. You could grow the bounds that you were considering in the neural network for until you found a program region that was well structured with this input and output behavior. So there might be lots of internal state and communication, but that you allied that. And in your example, you could have you have some inputs, which is the program, and then an output, which is, will this program halt, right? And you can try to train the neural network to do that. And that has well-structured inputs and outputs, but you're not going to be able to train a network to do it. So I think it's, to your point about the halting problem, I think it's really just that some functions are amenable to neural networks and some are not. And the less they're amenable, the more error you're going to get. And with the halting problem, you're just going to get pure entropy. You're going to get a random result, and you basically have zero signal there, because you can't train a network to do it. And so it's really just there's a spectrum of how much error you're going to have. And for some things, the error will be infinite, 1.
Usually it's random 0.5. You can have like random, like a neural network. If that's like a classification problem, you can have a random.
Right. So is that right, do you think?
Yeah, I think that is right. I mean, I think the idea is that if you have n inputs that you're training on, you're going to get some answer by the network. And if you use n+1, the entropy stays the same, or the amount of error stays the same. It doesn't go down, right?
Right.
As you add that training, and if you keep adding and adding and adding, you're never going to get to the position where you actually converge.
That's right. It's really just a question of how learnable is the function.
Yeah.
And the dimensionality of the space of the data, like the input. Right. If you grow the dimensionality, then training is going to be harder and harder.
So I have another question, and maybe you're going to get to it, but it kind of comes back to the algorithmic aspect. That if these applications know that they can tolerate a certain approximation in their results, where would changing the software implementation, not using your library to learn and train a neural network, but changing the implementation of the code to tolerate that much less quality in their result sit? right? I mean, I'm trying to get at the change that you get from invoking the neural network with some special hardware or whatever, right? Versus algorithmically doing less work and getting a less accurate.
So I can give you one example answer. So when I was doing JPEG, I downloaded the code of JPEG and I was using it. And when I did the Parrot transformation, I was getting like 100x speed up. The reason was that the DCT part of the JPEG was like a cosine, exact cosine transformation. And that's very, very slow. Then I changed the implementation. I found another implementation that DCT was approximation of the exact. And my speed up was around like 70%. So even at algorithmic level, you can do approximation, but there is a limit. And then this goes beyond that. The other thing is that we wrote another paper called, we proposed another architecture, which is changing the processor itself and supporting approximation instruction. That's one of the ways that you can deal with approximation. The gains that we were saying is that no speed up, yet like 20% to 40% energy reduction. So we were going after like 20% energy reduction. And here we are saying around like 2x speed up, 3x energy reduction when we are doing this. But one of my colleagues, Adrian, you know Adrian, so he's working on compiler optimization, unsafe compiler optimizations that you can apply to regions that are approximate and probably execute less code and see how much you can get away from that. I don't have a head-to-head comparison to that technique. So during my internship, so this is what I did before. So I started with generated code. Instead of using a library, I can actually get the neural network and generate a code, which is efficient. Then let's assume that one of the things that I'm going to show you the results and you're going to see. One of the things that causes this slowdown is the sigmoid function, which takes a large part. And then, like I finished it like 2 days ago, I did AVX Code Generation with Intel Ivy Bridge AVX extension to see if we can use vectorization and gain better results. So before I show you the results, I want to talk about the AVX Code Generation. So we can do vectorization in two different models. One is that each neuron is summing, multiplying and summing up. So I can use the parallelism inside the neuron and do the vectorization like this. Different inputs getting multiplied. Or I can do across neurons and just one input for different neurons in each vector. I took this because I think this is it gives a better vectorization approach when at the end I have to do a ladder of additions to get the final result. So I can do the additions for different neurons at the same time. I implemented this one. Let's look at the results. So before I show you the slowdown, a byproduct of doing this work is that actually, let's say we want to do neural network execution, regardless of Parrot transformation, how much gain we can gain with this technique. So this is speed up over the FANN library when you are doing neural network invocations. So this is the generated code. You get around 1.5x speed up, 50%. And when you add the sigmoid instruction, you see a huge bump, and the geometric mean speed up goes up around 7.3x. And then when you do the vectorization with vector support for sigmoid instruction, you get an order of magnitude speed up for neural execution.
Floats.
These are floats, single precision. And one thing that I found surprising is that AVX sometimes results in slowdowns for small networks, but this is the biggest network that I had, 18, 32, 8.2, and I see a huge bump here along 13x speed up over hardware sigmoid code generated. So this is the application slowdown when we apply these techniques. After I did the code generation and gained something, then after I added the sigmoid instruction to the processor, actually 2 of the applications see is speed up, even without any hardware support for neural execution, just the sigmoid instruction. And the factorization takes the slowdown from 15.7 to 2 point. So this kind of makes a case for using dedicated hardware to do the neural network execution. So I'm going to talk about the digital hardware implementation. So for this, we needed a configurable hardware that can realize different neural networks. Different regions of code require different neural networks. So the hardware implementation needs to be reconfigurable. Then we needed a microarchitectural interface between the accelerator and the processor. And we needed ISA extensions that can communicate with the NPU, lets the processor to communicate with the NPU. And at the end, I thought that I was talking about what this is like. So at the end, since we are doing very fine-grained acceleration, this integration of the hardware neural network should not hinder speculative execution or out-of-order execution in the processor. So we designed a reconfigurable NPU, digital NPU. Each neuron essentially is a multiply-add unit with weight cache and just crunches through the multiply and adds. And then with a sigmoid hardware sigmoid unit. And then these are the 3 FIFOs that are exposed to the processor. So the processor sends inputs and out to this FIFO, reads it from that FIFO, or configures and sends the weights to the NPU. So I used Mars x86 cycle accurate simulation. It's configured very closely to Intel Core architecture and an 8PE NPU. And I compiled the applications with -03 so that I don't bias the results by less part. So these are the application speedups. The dark part shows the actual speedup with the NPU that I showed you. The light bar shows the ideal speedup that I would have gotten if I had a 0 delay NPU. So I achieved 2.3 here. And one of the applications actually see, even with hardware, the slowdown, because that region of the code for K-means is the Euclidean distance calculation. It's a very fine region. It spends like 30% of the computation in there. So the actual implementation, even though the network is small, the actual code is very efficient. So, and I'm seeing around 3x slowdown, energy savings here for the applications. But I would have gotten 3.9x if I had a 0 energy NPU. So the question is that can we move this further? Can we push it further? This is actually analog NPU. So part of my internship, I studied the feasibility of moving toward analog implementation of neural networks. So to do that, so as I said, the ANPU needs to be reconfigurable. So what we are going to do here is that we are going to do the computation in analog and the storage and communication between the units of analog computation in digital. So we call each of the computational units that carry out the computations of a neuron an analog PE processing engine. So we have two. So we can have an array of APEs, analog PEs, and then we have to figure out how to map the neural network to it. So one is to time multiplex this, time multiplex neurons over the APEs. And that happens that we're going to do the computations of 1, 2, and 3 first, and then use the same PEs to do the 4, 5, right? The other approach is to have a two-dimensional array of APEs and geometrically map the neural network to this. The good opportunity with the geometric design is that the communication between the APEs can be analog instead of converting it to digital and then communicating it to the
That's not true. You can time multiplex it if you do a D to A and A to D conversion for the analog units.
You can do it, but here you don't have to do it.
But if you want to stay in the analog domain, then you need the multiplex design. The geometric design.
Yes.
Yeah.
Yes, exactly. And there are other factors like resource utilization and fault tolerance.
So I'm a software guy. Can you give me a little 2-second understanding as to why I would want to use analog rather than the digital experiments you've already
So the reason is that with the analog, you can do addition by just having a point here. Yeah. Like you have multiple wires coming to one point and use Kirchhoff law to do the addition. So you don't have to convert it to bits and things like that. And you can actually do the multiplication. Here we are not doing actually multiplication. We are scaling inputs. You can actually use a resistor ladder, pass a current through it, and use that resistors to scale that current and then do the addition. So you're just using the Kirchhoff law to do the multiplication and addition. That's much more efficient than doing the digital computation.
I think a broader answer is that in analog circuits, you can implement much more efficient computational primitives. I mean, you can do integration, addition, just by building a circuit that physically mimics the function. You just don't get digital precision.
Yeah.
So I have two wires with currents on them, and I tie them together, and that's an add. Yeah. It's pretty efficient.
There's a lot of work in that.
Yeah.
Arguably better.
What's that?
Get analog precision, which is arguably better in some scenarios.
Let's take that one offline. It's not wrong. It's complex.
So what we are going to do is we're going to have the communication between the neurons in digital, but the computations with the inside the APs and analog. So we have to decide how many inputs we're going to feed to that analog unit. Like perceptually, like theoretically, you can have multiple as any wires coming there to do the addition. But analog circuits tend to work in a certain small signal region. So you have this region of current that everything is linear and you're getting that addition effect. But if you blow out that region, then the nonlinearities in the analog circuit will kick in and screw your precision for that. So one of the things is the computation bits, how many inputs we are feeding to that analog P. The other thing is the number of bits that you're going to choose to represent any number. Right? With single precision, you have 32 bits. You have a very large dynamic range. But with the analog circuit, you are moving toward fixed point operations. And as you increase the number of bits, the speed, the energy is going to change drastically. I'm going to show you some results. Before I actually show you the results, I'm going to show you a little bit of the circuitry. So what we do, we convert the inputs, the bits, to currents. Right? You can have a switch and another switch which is 2 times the other switch, and 4 times, 8 times. And when you have ones in each position, then the current that goes through this these searches gets multiplied by that factor, and then you have a current value which is representative of that the bits that you had in the inputs, and then you can do the scaling or the multiplication with the resistor adder, and then do the, if you want to choose, you want to subtract or add, do the addition, you have to choose if you want to get the negative current or the positive current. And then so this unit does the multiplication for 8 inputs. And then you have the addition, which is just tying together the wires and getting it. And then you have the A to D conversion, which also applies the sigmoid naturally to it. And you get the output. So we went with the time multiplex ANPU design. This is a conceptual design. It's not like realized yet, but you have these APUs with 8 inputs. These are the input-output FIFOs, and then you do the communication digitally between these units. Our methodology for the design space exploration of this is that we are going to do cadence transistor level simulations and then feed it to a software simulator that realizes the entire ANPU. And the first thing that we did is to how far we can push the bit widths, right? We want to identify how much we can use bit widths. This is the single precision, and that's the error, right? And this is the number of bits for the inputs. And this is the number of bits for the weights, which goes through the resistor adder. You can see, it's like behind these lines, that 8-bit is enough, right? Okay, let's look at the energy projections. This is energy. This is the number of bits that you use in the AP. Because of the design of this digital to analog conversion, they said that the size of the searches are increasing exponentially. The energy is going to go exponentially as you increase the number of bits. So if we look here, this is 16-bit digital FP. This is the 16-bit digital FP, 2 different frequencies. Around 8 bits of input, we see it at 10x energy reduction. This is given the fact that we are doing A to D and D to A between the neurons and doing the energy, the communication in digital domain. If we do the geometric design, this is well beyond 100x, energy efficiency with analog. So for this, I have worked with Doug, Louise, and Professor Hasibi from UT Austin on the analog part. And I have also worked with the Adrian from University of Washington, Renee from University of Texas. And we have a new guy in University of Washington. Thierry is working on FPGA implementation of this so that we have a conceptual design that actually accelerates an ARM core, which is on the FPGA. We got the board and we are, pushing that forward. We have a web page for this project, and we're gonna, provide the compilation for flows, the tools that I developed for code generation of neural networks. I think that's important because, Google had this project that they did a very large scale neural network on their clusters. So the work that I did, which was toward using neural networks for accelerating general purpose code, but the byproduct of the code generation and using AVX and things like that can be beneficial for such projects when they are doing neural networks, or if Microsoft is interested in this. The thing that I didn't talk about is for the Microsoft mission, I was the compiler. But part of the internship was developing the compilation for workflow and doing it. Right now we are doing it pragma based, so the user uses pragma, and I did it more flexible to let the developer specify errors, ranges of inputs, or different things that can be used. And during my internships, I worked on the camera readies for these two papers as well. So that's all I've got. This is 5th day of creation. That's kind of where we are.
All right, so can I give you some advice about your talk?
Sure.
Because you're going to be giving a variant of this when you go out on the interview circuit. You should render this with the approximation. And end on that and not tell them, and then flip to the original and say, here's the version that was done digitally.
Okay.
Right? And then because every talk you give at a major university, people are going to jump on you and say, I don't believe you can give up error. How can you give up digital precision? Blah 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 blah. And they're probably right.
Mm-hmm.
So this will just, that little trick will sort of kind of anticipate that objection and head it off at the pass and say, well, as I've just shown you, there are cases where you can't tell the difference. I mean, you do it with the monkey, and you might want to leave that in, but that would be, it would just show that you've anticipated it, and then you can do it with a little smile, and that would be a really nice way to end it.
I have a question.
Sure.
If you go back to the slides where you have next one, this one, right, where you've got the energy. So you could use this to indicate how much the algorithmic changes would have to, right? How much you'd have to reduce the algorithmic complexity in order to match your energy savings.
Right.
Right?
Right. That's great. I'm a little bit, because we haven't done this implementation. We were planning to do it for ISCA this year, the analog implementation. So I was a little bit cautious about talking too much about it right now, but you're right.
I mean, because for example, JPEG's a good one because it's got the ability to tune it, right? It's built into the algorithm, right? To get the same 10% error that you had, right? If I set the quality factor at that, use that as the thing that you normalize to show what your energy savings are.
Sure.
Right?
Yeah,
So
that's
the
a good
algorithmic change is actually occurring, and you want to beat that,
Okay.
right?
So I'm curious if you thought about bubbling this up. The examples that you gave are very they're numerical, and the approximation is pretty obvious, right? And maybe this goes a little bit to Doug's point at the very beginning of the talk. There's a lot of situations now on the phone, for instance, where everything I sense, my phone is effectively sensing the world around me all the time. And all of my programming models that currently exist for that sensing data are discrete and work on facts, when the reality of the situation is that those sensors are not giving me factual input, right? They're telling me my approximate location.
That's exactly right.
And so I wonder if you thought about, how do you change, as a programmer, how do we start to talk about this? Error is great, but I don't think it's the right solution because it's very problem dependent. So how as a programmer do we start talking about dealing, bubbling this kind of approximation up to a programmer of the level of, the type of people that are writing JavaScript, right? How do we allow people who are writing these in these very high level APIs to reason about approximate computations? So this is a hard question. I'm just curious if you've given any thought to it.
Can I add to the question?
Please.
So I want to make the problem bigger. Okay. So if you're building an app for a mobile phone, and we're trying to do a lot of stuff in our group around inference and extraction of this high-level semantic signals from these noisy sensors and things you do like browse the web and all that. Okay. So we have a really good understanding of or appreciation for the problem. I think in this energy-limited world, in some sense, what you want to do, which we don't know how to do either, is give the programmer an energy budget and say, what's the best answer I can get with this energy budget? And it's not that your thing is going to add error. Your thing might allow them to do algorithms in that fixed energy budget to give a much better result with lower error. But if it's the digital representation versus the trained representation with error, it's exactly right. It's worse. But the answer is you'll be able to do much better stuff with this because you're energy limited, and so how do you say to the programmer, here's 100 joules and you want to figure out whether the user's at work or home, right? Now this will actually probably let them do a better job, but it's not about error, because the algorithm you would use if you had to do it digitally would have more error. I think that's what you're saying, right?
Yes, that's exactly right. Yep.
So in some sense, you want to give the user, the programmer, a bag of energy, and say, here you go. Now you have all these different choices you can do, and you kind of want to run it through a tool flow and say, this meets your energy budget, this doesn't, and maybe it's the discretization of your GPS sampling. Actually, I haven't seen any work on this, and this would be really cool.
Energy versus accuracy?
Giving a programmer in Visual Studio, you have an energy model and a model of the system and processor, and you have an energy budget.
Static.
Yeah, I have a static energy budget. You've got some, I provisioned, 1 million joules, and you have a template, you have a bunch of templates, sketches, right? And you compile the code, you'll do the analysis, you'll run it against the model, and then the system can automatically adjust, discretization of the data, number of loops, and scale the sketch down to meet your budget. And then you can say approach X, Y, Z, A, B, C, which one gives me the best results? That's what we're going to have to do in the future.
Yes, exactly.
And it's a compilation problem too, right?
It's a compilation problem. Actually, this would be a really interesting project.
Sounds like you're turning normal software into FPGA compilation in terms of and time enclosure.
No.
No,
I mean, there's an element of
It's
that.
approximate energy.
You've got a model,
Yeah.
but you've just got to expose the model.
Right.
Right. I mean, you can slice it two ways. You can say, here's, I can have some traces, I can do some profiling, I can take these different sketches and say, here's the quality answer you get, and here's the amount of energy that each of them consumes. And
It's
you want
something like
the,
gprof, which instead of giving you the timing that you spend in each function, gives you the amount of energy that you're going to spend.
it's eprof, energy and
Yes.
error.
Yeah.
It's like an e-prom.
Yes.
So we've started doing a piece of this, Catherine McKinley and myself, for the work we've been instrumenting Windows Phone to provide effectively exactly what you talked about as an energy budget.
Yep.
We haven't gotten to the point where, and then that budget then is used to inform, and it's predictive, you have to predict what the budget is for today. I think that normally you turn on your power, or I'm sorry, you plug in your phone at 6 o'clock at night.
Yep.
Right, and so that gives me now I look at the battery and now I say, okay, I've got an estimated amount of power that I have to get through the day.
Energy.
And then I'm sorry, energy, yes. And
Sorry,
then,
that's a pet peeve of mine.
and then you have to make decisions based on that, right? But
Yeah.
we're nowhere near, I think, the what you just described.
Yep.
Yeah. I think
So we're the
like
OS for that ecosystem that we did a long time ago. Do you know what that is?
I think I've heard of it, yeah.
Yeah.
So this,
Yeah.
I mean, hey, this
This
is all
was
coming
the
together. We have the right set of
capacity.
people in the room.
yeah,
To
and,
enforce it.
yeah.
You did a great job today, Hadi. Good talk.
Thank you.
It's a
Yeah.
great project.
Very exciting work.